You might remember a teacher saying a function has an inverse. Sorry, well, no, sorry. You might remember a teacher saying an equation is a function if every input has one output. What that means is if you plug in x equals 1, you can only get one output, y equals something. Okay, so this is an example of something that's a function. This is now an example of something that is not a function. It's a relation that's not a function. Okay, x equals 1 gives us two options, y is 2 and y is 4, so that's not a function. Now it's a function again. Okay, x equals 1 has one option, and it has to be true for every value. Now, something similar happens with inverse functions, except it's now going in the reverse direction. Every y value pairs up with only one x value. So look, this is a function we said. This is a function. Let's say y equals 3. And then this is, it's still a function. We're still talking about a function. Every value for x in this makeup function has one value for y. Now, these two are the same though. It's still a function because we can only draw one arrow from each x value. We're not drawing two arrows like that. Okay, so it's still a function, but now this is considered not a one-to-one function. Every value for y doesn't just pair up with one unique value of x. Y equals 4, here we could redraw this like this. Y equals 4 has two different partner x values. Graphically, what that means is if you graph a function, it needs to pass the horizontal line test. So this graph that I just drew here, every horizontal line you draw through my graph, it only touches once. Therefore, it is one-to-one and it has an inverse. Okay, that's the whole point of one-to-one is for this section is determining whether it has an inverse. So the function I'm drawing right now is not one-to-one because it fails the horizontal line test in a bunch of places, across at two places. So that means this function I just drew does not have an inverse function. So that's what you'll want to do with each of these. You want to graph them. At this point, I don't think we've reviewed the algebra steps you need for some of these to determine whether they have an inverse or not. So if you graph this function, you can use Desmos.com or a TI calculator, or I'm going to do it the old-fashioned way because I'm an old man. If I plug in 1 in for x, I get 5 for y. If I plug in 0 for x, I get 3 for y. I hope. Maybe I'm going too fast. If I plug in -2 for x, that's 1 plus 1 is 2. Have I done anything wrong yet? I don't think so. I can't plug in 2 in for x or I'll have it divide by 0. If I plug in 3 in for x, I don't know what I just pushed. 3 for x, that's -4 plus 1, that's -3 for y. If I plug in 4 for x, that's -2 plus 1, that's -1. Okay, that's probably enough to graph. Look, it's a rational function because x is in the denominator of a fraction. So the classic one is 1 over x. That function looks like this. We should be seeing something similar. It's just been shifted a little bit, okay? So if I make all my dots 0 and 3, it's roughly right there. -2 and 2 is roughly right there. 3 and -3 is roughly right there. 4 and -1 is roughly right there. It's starting to make that shape, right? The vertical asymptote at x equals 2, because that's where the divide by 0 problem happens. So the big point here is that it levels off. We never cross more than once with the horizontal line test. Here it starts looking like it might be getting close, but because there's a horizontal asymptote y equals 0, it never crosses. So this, yes, the answer, yes, it does have an inverse. Do the same thing with this one. Graph it with your fancy schmancy calculators or whatever you kids are into nowadays, and then you all go home and you practice with graphing calculators instead of playing video games, right? 2 to the third is 8. 8 minus 4 makes 4. Let's try plugging in negatives. That's -1 minus 1 is -2. If I plug in -2, that's -8 minus 4, that's -12. I'm doing it real fast because I know people following along with this video are going to be using the calculator. So 27 minus 9 is 18, I think. Okay, that's probably enough. So 0, 0 is a dot, 1, 0 is a dot, 2, what, dumb, stupid math. Yeah, wait, that's right. 2, 4 is, yeah, 2, 4 is a dot. -1 comma -2 is a dot, -2 comma -12 is a dot, and then it just starts getting out of control like that. So look, the highest power here is a cube. Okay, so a cube function looks something like this if it's just x cubed. Okay, but look, we can't do that in this one unless we make a perfectly horizontal line right here and then go back up. That's because when you adjust the cube function by like subtracting it by x or something like that, then you're creating another 0 for the function, another place where it can equal 0, like what we just got here. So what's actually happening is this is going up and then back. Wait. We've got to plug in 1 in between here. Let's plug in 1.5. So 1.5 cubed, 1.5 squared. Subtract, that's the opposite sign though, so that should be 1.25. So I plugged in, oh no, that's not the one I want. I want to do 0.5. Shoot. If I plug in 0.5, you're all skipping over this part of the video because you've already used the graphing calculator. So it's -1 point. So I plugged in 0.5 and I got something like this. So it dips down and then it goes back up. So there's our graph. The whole point, that's actually necessary. You have to have that part because look, it fails the one-to-one test right there. Fails the horizontal line test. This is not one-to-one. It does not have an inverse function. Okay, and then this graph, just go ahead and graph it in our graphing calculator. Makes a horizontal asymptote at y equals 0, and then all of a sudden starts getting really big. Doesn't fail the one-to-one test anywhere. So this does have an inverse.